Hello everyone, this is lecture 6, Analytic Methods of Model Fitting. So in this lecture, in lecture 7, we're going to look at different criteria that you can use to actually fit a curve into a collection of data points. Okay. So that's the idea, right? So the learning objective is investigate several criteria for fitting curves to a collection of data points. So the first criterion that we're going to look at is called the Chebyshev approximations criterion. So now you have in data points, again, you have a bunch of point, X component, Y component, and it's get presented here on the graph. So there are 4 points that you observe, A, B, C, and D, right? And you have a straight line here, which is the line or the model that we're going to build up to fit into this 4 points that you just observed. Okay, so the idea for the Chebyshev approximation criteria is to, right at the beginning here for this part of the lecture, is to fit the data point to the line y equal to ax plus b. So to fit the data point to the using the line y equal to ax plus b, and a is the slope of the line and b is the y-intercept. So let me quickly note that. So a is the slope and b is the y-intercept. Okay, so y-intercept means that's the line will cut to the y-axis at the point, and that point is the point 0, comma b, which is y-intercept. Right, so what we need to do to fit the data point using the line, right, or any curve for that matter, is to determine the parameter. The parameters A and B. So in this case, we're just dealing with a line that minimize the distance between any data point x sub I, y sub I, and the corresponding point on the line. Right, so the points on the lines are x sub I, and then you substitute x sub I into the line that we need to come up with. You obtain y sub I. So in this case, y sub I is of the form a times x sub I plus b. Right. So there are two things that you need to do with. Right. So the first is the data point that you collect, x sub I, y sub I. And the second thing that you need to provide in the problem is the point on the line that you come up with. Right? So this is the point on the line. So in this case, again, you go back to this graph. You have 4 points that you observed in your graph on the XY plane. A, B, C, D are the points. Now, it just happened that this straight line fit in this data point, and it kind of go through A, C, A and C. Right? So what we want to do is that we look for the parameters A and B that minimize the distance between any data point, right? So let's say you consider the point D, right? You want to minimize the distance between D and the point on the line, and the point on the line is this. Okay. More specifically, what you want to do is to minimize the largest absolute deviations so this is the notations y sub I minus y of x sub I over the entire collection of data points. Okay, so this means that what you do is you find A and B to minimize the max value of this distance. Okay. So let me quickly note that y sub I right here is the observed data point, right? And this value right here is from the model that you come up with, right? So these are two different values, right? And the distance, you need to calculate the distance. There are multiple points, there's multiple deviations. For example, the deviation between the point D and this point, the deviations between B and, if you have another point on the line at x2, right? So you need to calculate the deviations here as well. Things like that. Right. You calculate each deviations, you find the max, and then minimize that those values that you just calculate. So for this lecture, we just going to come up with the set of rules for this criterion in some example. Later on in the course, there's a technique called the linear programming technique. By then, we will learn how to find the solution to this type of problem, right? So again, for lecture 6, we're going to come up with some criterion to fit a curve into set of data points, but we're not going to find true solutions to the curve that we want to produce. However, later on in the course, we're going to revisit this particular problem, and then we learn how to actually solve for the solutions. Okay, so let me formally write down the definitions of Chebyshev approximations criterion. So given some function y equal to f of x, it can be anything really. It can be linear functions, can be quadratic functions, cubic functions. So any function for that matter. It's just that at the beginning, we just want to use the lines, so that is really easy for us to understand the process. So given some function y equal to f of x and a collections of n data points, x sub I, y sub I, for I is equal to 1, 2, up to n, because you have n data point. What we do is we determine the parameters of the functions y equal to f of x that minimize the number, so the max value of the absolute deviations or the distance between the observed data and the model, the data from the model. Right? Again, I is from 1, 2, up to n. Okay, so this is the definitions for the Chebyshev approximations criterion. Now we're gonna use this to calculate some in an example. Right? All right, so now you have this set of data points. So there are 3 data points. We want to fit the model y equal to cx. Right, so this is a linear line to the data set, right? Using Chebyshev criterion, but do not solve for C, right? Again, later on in the course, we will learn how to solve for the value of C. This is not as straightforward as you think. There are certain steps that we need to follow to actually obtain the value of C. All right, so to fit the model using Chebyshev criterion, we're going to insert the following questions, right? So the first part is to express the residual R1, R2, R3 corresponding to the data point, and you may ask what is the residual. So we're gonna give the definitions, and then I will walk you through the process of setting up the problem or formulate the problem more properly. Okay, so residual means that so represent the discrepancy between the two and measure values, right? So in this case, the residual that we have is the discrepancy between the observed data and the data you get from the model. Okay, and now we set up that here you have 3 data points. So you have n equal to 3, right? What we want to do is we want to determine the value of C that minimize the max value of y sub I minus f sub xi. In this case, the functions you have is C times x. So what you want to do is you minimize the max of the absolute deviations of y sub I minus C times x sub I. Okay, so this is the discrepancy between the observed data and the data you collect from the model and you get from the model. And because of this discrepancy, we call that the residual, right? And this is the max residual. So I'm gonna let this equal to R, right? So that is where this R coming from. Okay, now you go back to the data, the table of data. All right, so I'm gonna make a table here. I'm gonna have 3 columns. One column is for X, one column is for Y, and one column is for the calculations of y sub I minus c x sub I. So y sub I minus c times x sub I. So the x values are 1, 2, 3. The corresponding y values are 2, 5, and 8. So y sub I is, right, so y1 is 2, y2 is 5, y3 is 8, and x1 is 1, x2 is 2, and x3 is 3. So you do the calculations here. So 2 minus c times 1, you got 2 minus c. And again, this is the discrepancy between the observed value and or the observed data and the data you collect from or you get from the model. So I call this R1, right? The first residual or residual of the first data set, or the first residual of the first data point. Now for the second data point, you get 5 minus c times 2 or 5 minus 2c, you call this R2. And the last data point, you have 8 minus c times 3 or 8 minus 3c equal to R3, right? So again, you say that where R1, R2, R3 represent the discrepancy between the observed data and the data from the model. So now you have three different residual, right? Or three different um, absolute deviations. So now again, you reformulate this statement instead of determine the value of C that minimize the max of this absolute deviations. What you can formulate is that we want to determine C that minimize the max value of this three residual. Right. And we let this max value to be equal to R, right? Very similar to this case. Okay. All right, so how could you formulate the problem so that later on you can solve for the value of C? Again, this is not as straightforward as you may think. Okay, so now that's the first part. Part A express the three residual R1, R2, R3 corresponding to the data points. You get that, and then you'll formulate the problem more properly. Now B, if we use R to be the largest absolute deviations, right, which we did here, we don't know the value of R1, or we don't know the value of R2, or we don't know the value of R3 at this point, but we just want to find the maximum among these 3 points, among these three residual, and that maximum, we call that R. Okay, so now we use R to be the largest absolute deviations. What is the relationship between the residual R1, R2, R3 and the maximum residual? Okay, so that's part B. Okay, so so R is the maximum value. That's for sure, right? And we don't know about R1, R2, R3, but we know for a fact that R1, R2, R3 has to be less than or equal to R. That makes sense, right? Because R is the maximum value. But not only R, but you have the distance between R1 with 0 to be less than or equal to R. So rather than that, just R1 less than or equal to R, I have an absolute value of R1 less than or equal to R, or the distance between R1 and 0. Right? So let me draw this on the real line here. You have 0 here, you have this is negative R1, this is positive R1. I don't know about R1, right? But I just know that the absolute value, if you just consider the positive part of that, then R1, sorry, this is R1. So R1 is greater than 0, or absolute value of R1 is greater than 0, but is always less than or equal to R. Makes sense, again, because R is the maximum residual. And we do the same for R2. Right, I don't know the exact value of R2, but I know that the absolute value of R2 is going to be less than or equal to R. And the same for R3. Right, so that's the relationship between each residual with the maximum residual. Okay, now we're going to jump into more detail of these three inequalities to set up some inequalities that help me solve for the value of C, or find this value of C such that I can minimize the maximum of the residual, right? So I have the first part here, absolute value of R1 is less than or equal to R. Let me do this over here. So the first part is our absolute value of R1 is less than or equal to R, or you can write that negative R1 less than or equal to, sorry, negative R less than or equal to R1 less than or equal to R. Right. So because if you take into account negative R1 as well, right? So R1 can be vary, right? So you can move among this distance, right? And it's always, if you have R, which is greater than R1 is less than or equal to R, then negative R1 is greater than or equal to negative R. And therefore you can solve that from this line. You can see that R1 is between negative R and positive R. Right? With the same argument, for the case of R2, you have that R2 is between negative R and positive R. And for R3, you have R3 is between or greater than or equal to negative R and less than or equal to positive R. Okay. More specifically, you have negative R less than or equal to R1 less than or equal to R. There are two parts to this inequality. You have negative R less than or equal to R1, and R1 is less than or equal to positive R. So I just basically break this inequality into two different parts. And I'm going to substitute in R1. What is R1? So R1 is 2 minus C. What is R2? Is 5 minus 2C. And R3 is 8 minus 3C. I'm going to substitute this value of R1, R2, and R3 into the inequality I just got to find the relationship between R and the value of C. Okay, so R remains, sorry, I'm going to move it to the right-hand side so that I get R plus R1 greater than or equal to 0. And simultaneously, I can move R1 to the right-hand side. I got R minus R1 greater than or equal to 0. So these are the two inequalities I want to have. So again, substitute R1 into the inequalities. I got R plus 2 minus C is greater than or equal to 0. And at the same time, R minus 2 minus C. Right. Then I can distribute the negative. I got R minus 2 plus C greater than or equal to 0. So these are the two equations. Two inequalities I need to set up so that later on I can solve for the value of R or the value of C such that I minimize the value of R. Now the second inequality is negative R less than or equal to R2 less than or equal to R. Again, I'm going to break this inequality into two different parts. Negative R less than or equal to R2 and R2 less than or equal to R. So for this inequality, I move negative R to the right-hand side. I got R plus R2 greater than or equal to 0. And for this inequality, I get R minus R2 greater than or equal to 0. Now for R2, R2 is equal to 5 minus 2C. So I get R plus 5 minus 2C greater than or equal to 0. And R minus 5 minus 2C greater than or equal to 0. And then you distribute negative into the parentheses, you get R minus 5 plus 2C greater than or equal to 0. Now this is the third equation, the third inequality, the fourth inequality that we're going to use to get C in R. Then for the last inequality, you get negative R less than or equal to R3 less than or equal to R. Again, you break this down into two different parts. Negative R less than or equal to R and R3 less than or equal to R. So this And from the inequality I just wrote down, I get R plus R3 greater than or equal to 0. And R minus R3 greater than or equal to 0. Where R3 is equal to 8 minus 3C. So R plus A minus 3C greater than or equal to 0. And R minus 8 minus 3C greater than or equal to 0. Again, you distribute the negative, you get 8R minus 8 plus 3C greater than or equal to 0. So this is the fifth inequality. This is the sixth inequality. And this six inequalities, I'm going to use that to obtain the value of C such that I can minimize the value of R. Okay, so that's the setup. That's the formulations that you need to build up so that later on in the course, you will learn the technique to solve for this inequality. Again, this is not as straightforward as you may think. Okay, so that's it for the setup. That's it for the example, because I just want to make this formulate the problem in a way that later on we can solve for it. Okay, so let's quickly recap what we learned in this example. So in this example, the idea is to fit a curve, or rather the model y equal to cx into the data set using the Chebyshev criterion. Okay, what you do is you actually create a table of values where you have the x value, the y value, and the deviations. Right? We don't know the exact value of R1, R2, and R3 because we don't know the value of C. So we want to find the maximum of R1, R2, and R3. And the maximum, we call that R. Okay. And we're going to build the relationship between R1, R2, R3 with R using these inequalities. And for each inequality, we're going to put in the value of C so that we build up a relationship between the value of C, that's what we're looking for, that can minimize the maximum of the residual that we come up with earlier. Okay, so hopefully that gives you some idea how to perform the calculations and formulate the problem in a way that we can solve for the solutions later on. Now for the next example is we're going to do a very similar approach here, but instead of a straight line, now you have a quadratic functions, right? Of the form y equal to c times x squared. We're going to use Chebyshev criterion to deal with the model. We're going to build the 4 residual because we have 4 data points in this problem. I'm going to build up the relationship between R, the largest absolute deviations, with the residual that you get in part A. Okay, so here we have 4 data points. So here we have n equal to 4, right? So we want to determine the value of C that minimize the max of absolute value of y sub I minus f times x sub I. Right, so the function f in this case is c times x squared. In other words, you want to minimize the maximum of y sub I minus c times x sub I squared. Right, and I call this R because that's the largest absolute deviations or the maximum. Right. Now you set up the table just like earlier. Remember, you have 4 points in this case. I'm going to make 3 columns. The first column is the x value, the second column is the y value, and the third column is the calculations of y sub I minus c times x sub I square. Right, so this is the calculations that I need to build. So 4 points, right? So the first point is 0.5, 0.7. The second point is 1.0, 3.4. Let me separate them by this. The third point is 1.5, 7.2. So this is 2.0, 12.4. So y sub I minus c times x sub I square. That means you do 0.7 minus c times 0.5 square. By quick calculations, give me 0.7 minus 0.25c, and I call this R1, so the residual for the first data point. The next data point, you have 3.4 minus c times 1 square. Well, this is 3.4 minus c, call this R2. The next point, 7.2 minus c times 1.5 square. By your quick calculations, 1.5 square is 2.25. This is 7.2 minus 2.25c. Set this equal to R3. And the next point is 12.4 minus c times 2.0 square, or 12.4 minus 4c equal to R4. So you have four residuals that you build. So we want to quickly note that R1, R2, R3, and R4 are the discrepancy between the observed data and the data from the model. Okay, now we have value of R1, R2, R3, and R4, even though we don't know exactly, but we actually have the formulations of the residual. We can formulate the problem in this way. Right? So what we want to do is we want to find C and then minimize the value, the max of R1, R2, R3, R4, and I call this maximum value R. And from this setup, we come up with four different inequalities. That is R1, absolute value of R1 is less than or equal to R, or R1 is greater than or equal to negative R and less than or equal to R. R2 is less than or equal to R, or negative R less than or equal to R2 less than or equal to R. And R3, absolute value of R3 less than or equal to R, or R3 is between negative R and positive R. And R4 is less than or equal to R, or R4 is greater than or equal to negative R and less than or equal to R. All right, now for each inequality, you break down into two different inequality, then you put in the value of R1, R2, and R3, and R4, so that you can build the relationship between the value of C and R. So for the first inequality, negative R less than or equal to R1 less than or equal to R. You have negative R less than or equal to R1 and R1 is less than or equal to R. Or you move negative R to the right hand side, you get R plus R1 greater than or equal to 0 and R minus R1 greater than or equal to 0. And R1 is equal to 0.7 minus 0.25C. So you get R plus 0.7 minus 0.25 c is greater than or equal to 0, and minus 0.7 minus 0.25 c greater than or equal to 0. Now you distribute the negative into the parentheses. You get r minus 0.7 plus 0.25 c greater than or equal to 0. So this is the first inequality that we're going to use. This is the second inequality that we're going to use. All right, so I'm gonna stop right here for the example. It's very repetitive in terms of breaking this type of inequalities into two different inequalities and put in the information of R1, R2, R3, and R4 into the inequality to come up with the relationship between R and C, right? So for the rest of the problem, I ask you to do that as a practice because it's very repetitive it's very similar to what we just did for this case and in the previous example. Okay, then let me move on to another criteria. Again, we're just going to write down the information, set up the problem or formulate the problem, but not going to solve the problem completely. Okay. And of course, the solutions of this example will be on Blackboard. Okay, so the next criterion that we're going to look at is the sum of the absolute deviations. Okay, so the Chebyshev criteria, it just you want to minimize the maximum of the absolute deviations. Here you want to minimize the sum of the absolute deviations. Now, if you look at this graph, right, the dashed line is the line that you get from the model, and the orange points are the data points that you observe. You plot them together, and you will see that this point and the corresponding point on the model have some deviations. What you're going to do is you're going to calculate each deviations, add them together, and you minimize that sum of absolute deviations. Okay. So that's the idea of this criterion. So given some functions, y equal to f of x, and a collection of n data points, x sub I comma y sub I for I equal to 1, 2, up to n. We want to minimize the sum of the absolute deviations. So that is find the parameters of y equal to f of x that minimize the sum of the absolute deviations. So for I going from 1 to n, right? So this is the absolute deviations. In the last case, which is the Chebyshev criterion, you have the maximum of the absolute deviations. In this case, you have the sum. So this sigma notation is mean sum of the absolute deviations. Okay, the sum means you just have a bunch of number and add them up together. Okay, so let's set up the problem. In this example, you go back to the data point or the data set of 1, 2 to find 3, 8, and you fit the model y equal to cx to the data set using the sum of the absolute deviations criterion. So here's the setup. Right, so you have again 3 residuals that you need to build up. So because you have 3 data points, so this is x, this is y sub I minus c sub x, c times x sub I. This is 1, 2, 2, 5, 3, 8. So the first deviation is 2 minus c. The second deviation is 5 minus 2c equal to R2. And the last deviation is 8 minus 3c equal to R3. All right. So the residual that you want to minimize is the sum, right, of the absolute deviations. So in this case, I is going from 1 to 3 because you have 3 points. So I going from 1 to 3. Right. And the setup going to be R. Right. So we want to minimize this. So R now equal to, because you have the sum, you have y1 minus c times x1 plus y2 minus c times x2 plus absolute value of y3 minus c times x3. Right? And you have 2 minus c plus absolute value of 5 minus 2c plus absolute value of a minus 3c. Or rather, you want to minimize absolute value of R1 plus absolute of R2 plus absolute value of R3. So that's the setup. So that's it for me for this lecture. In this lecture, we look at 2 criterion to fit a model to the data set or the collection of data points. The first one is the Chebyshev criterion, so that you minimize the maximum of absolute deviations. And the second criterion is that you minimize the sum of the absolute deviations. So that's it for me. Please let me know if you have any questions. Thank you.